Hi, folks. How y'all doing? Thank you for putting up with the video today while I am away. I will see you on Friday. We're going to start with the section on the inclusion-exclusion principle, and we're going to start with an example that should be familiar because it's similar to something we've done before. So this is out of the book. This is chapter 10.2.3. There are 4,000 students at Modern University, and they all own either a tablet or a smartwatch or both. So we are dealing with an inclusive or here. Surveys show that 3,500 students own a tablet and 1,000 students own a smartwatch. How many students own both? So if we think of this as a Venn diagram problem, we can solve it this way. And if we divide these two sets into three disjoint pieces, we'll call this piece A, call this piece B, and call this piece C, then the 3,500 students that own a tablet are A plus B, and the 1,000 students that own a smartwatch are B plus C, and the 4,000 students total is all three of them, A plus B plus C. And we can think of this as an equation, system of equations and three unknowns, and pull out our old linear algebra skills and solve this. But I think the easy way to proceed is to recognize that the second and the third equations both have a B plus C in them. And so if we subtract them, A plus B plus C equals 4,000. B plus C equals 1,000. And subtract, we just get A equals 3,000. And then after that, everything sort of falls into place. There are 3,500 students that own a tablet, and so there are 500 students in the middle piece. 1,000 students own a smartwatch, so there are another 500 students over in C, and therefore the number of students that own both a tablet and a smartwatch is B, which is 500 students. All right. What we're going to see today is an alternate way of handling the inclusive or without having to draw a Venn diagram. And so this is called the inclusion-exclusion principle. So we've dealt previously that multiplication corresponds to and, addition corresponds to XOR, and inclusive or requires that we do something different because of the shared intersection and make sure we don't double count it. So in an inclusive OR situation, when we have two sets, we could divide this into three pieces and think about the three pieces together. But the other way we can do this is we can think about the set A and go ahead and count everything in A. So we're counting everything in set A. Now, one of those wasn't in set A. There we go. And then we can count everything in set B. But then the part in the middle has been counted twice. And so if we subtract the part that we counted twice, subtract once, so that it's counted once, then all of the terms have been counted one time. And this formula here gives us an idea for how to count the two sets. We count the sets one at a time. And then we take the sets 2 at a time. But we change the sign when we switch from 1 to 2. And that seems a complicated way of saying we add these two and we subtract the intersection. But I want to show you how the pattern expands to 3 sets now. So we're going to look at a 3-set problem. What if we have 3 sets? Well, we can start by counting everything in A, and everything in B, and everything in C. So when we count A, we are counting this piece, and this piece, and this piece, and this piece. All of those 4 pieces make up A. Then when we count B, we're counting these 4 pieces. And then when we're counting C, we count these 4 pieces. But we've counted the intersections multiple times. So what we're going to do now is we're going to subtract those intersections. So we're going to subtract A intersect B, and subtract A intersect C, and subtract B intersect C. And when we do that, subtracting A intersect B takes away one of the counts of those 2 pieces there, the 2 pieces where A and B overlap. Subtracting A and C take away these 2 pieces, and subtracting B intersect C takes away these 2 pieces. And now this piece has only been counted 1 time, this piece has been counted 1 time, this piece has been counted 1 time, but the piece in the center, we have undone all 3 of the counts. We counted it 3 times, and then we deleted it 3 times, and so now it hasn't been counted at all. And so we're going to have to add that 1 piece back in. We're going to have to add back in the pieces in the dead center to make sure that it got counted 1 time. And so the pattern for 3 sets is we take the sets 1 at a time, then we take the sets 2 at a time, and then finally we take the sets 3 at a time, and we change signs every time we move to a new number. So we add the sets that we take 1 at a time, but we subtract the sets that we take 2 at a time, and then we add the sets that we take 3 at a time. There's a sign change at every level. On Friday, we're going to do a 4-set problem, and this pattern will continue, where we add 1 at a time, subtract 2 at a time, add 3 at a time, subtract 4 at a time. And it will be very doable, but it will be a little complicated because of all of the different parts to the problem. But if you understand this principle, you should be able to follow along on Friday. What I'd like to do in the time that we've got left is just work through a couple of examples, and we will wrap up. All right. So this example, we have the College of Science. Every faculty member can mark as many boxes as they wish on their ballots. You don't just have to vote for 1. And there are 3 professors that are working on a position on the department search committee. Lee, Chung, and Osborne. And again, faculty can choose more than 1 if they want to choose more than 1 of the candidates. Barb Hodgson notes the following facts. These are on the next slide when counting the ballots. Chung received 18 votes. Osborne received 15 votes. Lee received 10 votes. 1 ballot had all 3 boxes marked. 5 were marked for Osborne and Lee. 10 were marked for Chung and Osborne. 6 were marked for Chung and Lee. How many members of the department voted in the election? So this is our question. I'm going to try this problem in two ways. We're going to do this using a Venn diagram, and then we're going to use this solving this using the inclusion-exclusion formula, just to demonstrate that both methods lead to the correct answer. So that you have two different tools in your toolbox for solving this kind of question. So let's start with the Venn diagram. We have three circles here: Chung, Osborne, and Lee. And we'll start from the inside. There's one ballot that had all three boxes marked. So there's one in the very center. We know that 5 ballots say Osborne and Lee on it. And we already have one marked for Osborne and Lee. That's the one in the center that's marked for all 3 of them. And so there are 4 more ballots that are marked for just Osborne and Lee, but not Chung. And that's not Osborne and Lee. Osborne and Lee is over here. Sorry. Put it in the right place. 10 ballots were marked for Chung and Osborne. That's the spot that goes here. 9 and 1 will make 10. 6 ballots were marked for Chung and Lee. 5 and 1 make 6. And so now these pieces are taken care of. So let's go back to the top. Chung received 18 votes. And so far we have 5 plus 1 plus 9. That's 15 votes. And so we need 3 more votes to make up the total of 18. Osborne received 15 votes. Well, 9 plus 1 plus 4 is 14. And so Osborne needs 1 more vote to bring the total up to 15. And Lee received 10 votes, but 5 plus 1 plus 4 already is 10. And so Lee does not need any additional votes just for himself. All right. And so how many members of the department voted in the election? Well, that would be 3 plus 5 plus 9 plus 1 plus 4 plus 1. So 3 and 5 is 8. 8 and 9 is 17. Plus 1 is 18. 18 plus 4 is 22. 22 plus 1 is 23. 23 people. So that's the Venn diagram solution. So here's the solution using the inclusion-exclusion law. We're going to add all of the numbers that represent taking the professors one at a time. So just by himself, Chung received 18 votes. Osborne received 15, and Lee received 10. Then we change signs, and we look at all of the numbers that represent the faculty members taken 2 at a time. 5 for Osborne and Lee, 10 for Chung and Osborne, 6 for Chung and Lee. So taking it 2 at a time, we have 5 plus 10 plus 6. And then we change signs again, and we now look at the professor taken 3 at a time, and there's only 1 ballot for all 3 professors. So let's add these together. 18 plus 15 plus 10 is 33 plus 10 is 43. 5 plus 10 plus 6 is 15 plus 6 is 21 plus 1. 43 minus 21 is 22. 22 plus 1 is 23 people. And so once again, we have now 2 ways of solving this problem, both of which add up to the exact value that we want. And whichever method is more comfortable to you, you're welcome to use that method, but having multiple tools in your toolbox make you stronger at what you do. So let's do one more problem, and we will wrap this up. So how many numbers between 1 and 5,000 are divisible by 3 or 17. So I will show you the Venn diagram. These numbers are divisible by 3. These numbers are divisible by 17. But there are some numbers that are divisible by both 3 and 17, which means that they are divisible by 51. Okay? So if we want to count all the numbers that are divisible by 3, those include 3, 6, 9, all the way up to 4998 is the last number that's divisible by 3 in this list. The way we could count them quickly is to divide by 5,000, and we're going to have a remainder because 5,000 is not divisible by 3, but we can discard the remainder, and then we would get the number. Discarding the remainder, we sometimes call that the floor function, and we notate it this way. It would be 5,000 over 3, and then take the integer that's lower than that. Drop the fraction. All right. We're still working on one at a time, taking now the 17. So we will do 5,000 divided by 17 and drop any fraction that we get. And now we'll take the numbers 2 at a time. We're going to subtract, and we're going to look at the numbers that are divisible by both 3 and 17 now. The original problem is asking about the inclusive OR, but the intersection is 3 and 17, and is multiplication. And so we are multiplying here, or you could just think of it as if you're divisible by 3 and 17, then you're divisible by 51. But here's another case where and indicates multiplication. And so we just calculate this out. 5,000 divided by 3, drop the fraction, is 1666, plus 294 minus 98, and that leaves us with a grand total of 1862. And so the total number of integers that are between 1 and 5,000 that are divisible by 3 or 17, or both, is 1,862. And at this point, we're going to go ahead and wrap up. I will see you Friday. Bring questions, and we will tackle the roller coaster train log ride problem that's at the end of this packet of notes. Have a great couple of days. Take care.